Alrighty, hello everyone. My name is Zach Blumenfeld. I am a graph data science specialist here at Neo4j, and today we are going to be talking about supervised entity resolution. And specifically, we are going to be exploring supervised entity resolution within the context of graph and Neo4j. So for our agenda, we are going to start out with an overview. I want to take some time to cover entity resolution at a high level in case you're unfamiliar. From there, I want to cover link prediction pipelines, which will be our mechanism for supervised learning, and we're going to be doing that inside of Neo4j's Graph Data Science Library, also called GDS. After that, I want to spend most of our time here with real-world data, so we're going to go through a demo and spend the majority of our time on that demo. That will start with reviewing the data source, the original data source that we'll be using. From there, I will jump into the Neo4j browser. I'm going to show you how to do feature engineering, set up a link prediction pipeline, and train a link prediction model. We are then going to use that model to predict new entity linkages inside of the graph, and then I'll show you how to assign resolved entity IDs on that basis and also be able to very quickly query resolved entities out of the graph. After that, for the final step, we'll go over some follow-up resources. So I will link you to a GitHub repository that should have everything you need to reproduce the demo we'll go over. And I'll also be going over some technical documentation as well as some follow-up in terms of graph and Neo4j and use cases around entity resolution. What I'm really hoping that I'll be able to communicate here is just how much easier Neo4j with GDS makes some of these graph analytics problems. In practice, I know that supervised entity resolution sounds nice, but it's not always the easiest thing to apply. It can be tricky to figure out how to really use it in an enterprise context and scale. The great thing about Neo4j with GDS and the way it's structured is that it takes care of a lot of the complexities around managing graph data, being able to quickly move data from the database into an analytics environment, and taking care of the nitty-gritty in terms of formatting your data, feature engineering inside of graph, being able to run and actually implement graph algorithms globally, and setting up a good pipeline. So it really allows the data scientists to focus on the high-level sequencing of the pipeline and the overall modeling strategy. So while what we're going to go over here is just an exploratory demo, I'm really hoping that whether you're a beginner data scientist, someone who's been doing this for a while, or a business leader in this space, that we can really show how this tooling can reduce friction for analysis, allowing you to get to answers faster, and really giving you a way to prototype, develop models quickly with a clear path to production, reducing a lot of the common bottlenecks and risks that pop up with graph analytics along the way. So with that, we'll go ahead and get started with our overview. Getting started with entity resolution, if you're unfamiliar, entity resolution is basically just the process of disambiguating data to determine if multiple records actually represent the same real-world entity, like a person, an organization, a place, or really any other type of object. And this is something that comes up a lot in industry and often for data science as well. And it stems from the fact that we're not always in control of the number of data sources that we have to feed our analysis, as well as the quality between those data sources and the consistency between those data sources. And in some circumstances, when you're interested in analyzing a user or a business or really any other type of entity, it can be difficult to connect the data together because the identifiers that you would ordinarily rely on are either going to be sparse or poorly formatted or inconsistently formatted or all of the above. And without some sort of entity resolution methodology inside of your process, it can really hinder the quality of your analytics and the insights that you want to deliver. So this is something that we see, for example, in online advertising, where people might have non-persistent identities online, and it can be difficult to form comprehensive user profiles that you need to effectively target an audience. Also for things like search recommendation, where you're trying to improve user experience and really create a full sort of customer 360 profile. And in the public sector, for things like law enforcement, where you're interested in collecting information on aliases, collating a lot of evidence together, and creating comprehensive reports around persons and organizations. So oftentimes, graph ends up being a really great solution to perform entity resolution, and that's because inside of graph, you can very naturally model connections between the entities you're interested in using relationships and nodes. So for example, here you see that I have two users. They're connected in this case by a common IP location that they share, maybe their web browsing activity. Also, even though I don't have it shown here, you can represent phone numbers as nodes, names, email addresses, really any identifier you want. And that allows you to create sort of these natural connections between entities. And from that connectivity in the graph, you can then make entity resolution inferences. And you can represent those as entity linkage relationships. So for example, in this case, I can have what I'm calling a same as relationship going from one user to another user that denotes that I either know or believe that these two users are actually the same underlying entity represented twice. And as you build on that, you can do this multiple times and connect multiple users or other types of entities together. And these create these clusters, or what we would call components, which then you can assign an entity ID. So for example, because these three users I have here are connected, I would call them all person one, and then other users and other connected components I can assign different IDs. So person 2, 3, and so on and so forth. And that can be used to further aggregate information and create comprehensive entity views. So I wanted to take some time to go over some more broadly methods for entity resolution inside a graph. I'm focusing on supervised entity resolution here, but I wanted to go back and cover some other bases just so that you get a comprehensive picture. So first, Cypher queries. So with Cypher, you can match different subgraph patterns inside of the graph and create business rules and logic around that will allow you to essentially scan the graph and assign different entity relationship inferences. So for example, maybe you have some business rules around whether or not two entities share the same phone number or share the same email address. Or maybe if they share multiple identifiers at once, it's a much stronger signal that they may actually be representing the same underlying entity. And so Cypher queries, especially when you're exploring and also when you have a very simple data model, those can be useful to apply and scan over the graph and get to an answer. Outside of that, to scale up a little bit, if you're interested in running graph algorithms globally, so basically running global algorithms on top of the entire graph, or big portions of the graph in sort of an unsupervised manner. There's a couple algorithms that are provided through the graph data science library for that. So for example, similarity algorithms, things like k nearest neighbor, where you can determine pairwise if nodes are relatively similar in the graph, and you can traverse out a certain number of steps. And that allows you to, in an unsupervised manner, create entity resolution insights, as well as things like community detection, which is really saying, well, if you have clusters of entities or components that are located around specific identifiers, you can make inferences around those entities either being their own hidden community or in some cases representing the same underlying single entities or set of entities. And then finally, what we're going to work on today is supervised entity resolution, and we're using link prediction for this. And this is where you train a model to predict entity linkages based on labeled data. And that labeled data is important. So because it's a supervised model, you need some labeled ground truth to be able to train it. And in this case, that's going to be the pre-identified entity linkages. So it's going to be basically some same as relationships that we already have pre-labeled. Okay, so from there, jumping into link prediction. So link prediction at a high level, it's pretty self-explanatory. The aim is to be able to predict where links should exist between different nodes in the graph. Your inputs for that model are going to be features inside of the nodes, as well sometimes as features that you engineer from the relationships in the graph. So using centrality metrics or things like embeddings, which we'll get into in our example. And Also as well, like I said before, in this form of link prediction that we're doing, you're going to need pre-labeled data, which in this case are going to be entity linkages that we can use to train on. So some of the challenges with link prediction, there are quite a few, and I have some here. So starting out at number 1, sampling and imbalanced data. So if you think about a very simple graph, right? Like say you have 100 users. The number of connections, entity linkages, the maximum number that you can have between 100 users is 100 times 99 divided by 2. So it's like 100 squared divided by 2, which is a gigantic number. And it's far, far larger than the number of entity linkages that would normally exist inside of that graph for most types of entity resolution problems. And what this creates is a really largely imbalanced data set where there are way more negative examples than there are positive examples. So it can be challenging with link prediction to figure out how to properly sample the data, and then also how to properly score a model, since there's certain scoring techniques that are better for data sets that are highly imbalanced. The second one on this list is data leakage. So when doing link prediction models, oftentimes you're interested in engineering features based on the structure of the graph, but the structure of the graph also includes those pre-labeled entity links that I was talking about. And so if you're not careful, you can end up in this scenario where you use the output, the thing you're trying to predict, in engineering your features, and that creates a scenario where your model's cheating. So the model may look like it performs well, but then when you actually try to predict on new data, the performance will crash if it's really using those features strongly. And then the last one is performance, and in a lot of ways it stems from the other two above, where it can be slow to figure out how to engineer the features, how to train and do this test splitting appropriately, and handle the data leakage issues. So there's lots of performance problems that come up with that. The great thing is that GDS has recently implemented link prediction pipelines. And what these do is they take care of a lot of the nitty-gritty associated with the issues that we were talking about, like the imbalanced data set problem, the data leakage issues, and it allows you to define a sequence of steps in a pipeline at a high level. So how to split the sample, how to generate your features, being able to train and compare different hyperparameters for different models, select the best ones, and then quickly be able to apply that, predict new connections, and cast that back to the database. So it really helps kind of simplify the process, and we're going to be going through that in our demo here in just a bit. So that about covers the overview, and from here we will go into the demo. The dataset that we'll be using for the demo comes from a Codalab competition around cross-device entity linking. The dataset itself is provided by the Data-Centric Alliance. You can think of the dataset sort of like a series of browsing logs where you have users getting hits on different URLs and HTML pages. More or less sort of like users browsing over different websites. I do want to take a look at a sample of the dataset just so you have an understanding. One of the most important files is this facts.json, and every record contains two key components. So this is a sample record. It contains this UID, which stands for a user ID, and you can see this is somewhat obfuscated ID. It's kind of like a hash. And then you have this thing called a facts array. And each element inside of the facts array contains an event and a timestamp. And these events are mapped to other online identifiers. So we have this URL CSV, and this maps the event ID over to a URL. And this URL, sort of like the user ID, is hashed. You can see here, though, that we still have these paths. So the URL segment the URL segments are we've still preserved the order between URL segments. And you see this one, for example, has a query string. It's just that the actual words or phrases inside of the URL segments are hashed, they're anonymized. Likewise, we have a title CSV, which is a similar concept where we have the event ID here, and then the hashed HTML title. For this demo, we're actually not going to touch the titles at all. We're just going to focus on URLs for now. One of the crucially important facts about this data set, and really where the challenge arises, is that these user IDs are transient. So if I were to use multiple devices and or log on at different times, I could potentially have multiple user IDs. And for this example, which is really focused around online advertising, the challenge, the goal is to use entity resolution to be able to infer all of a person's user ID, so you have a more comprehensive view of a person and can therefore target more effectively. Crucially, this data set also has a training file, so this contains the entity linkages between users, the pre-labeled data that we were talking about earlier, that lets us train a supervised model. Now, one of the other sort of odd things about this data set is that beyond this user ID, there aren't any other user identifiers. So there's no like names, usernames, emails, phone numbers, locations, anything like that. And that's unusual actually for an entity resolution problem. Most of the time you have at least some of those. But we'll see what's interesting is actually once you map this activity over to a graph structure, we can get pretty far training an entity linkage model to just based on the user behavior, make entity linkage inferences, which I personally think is super awesome. So we will go ahead and jump into that. So I'm going to go ahead and jump into the Neo4j browser. So we'll see what a sample of this data looks like in graph, and we will jump into the feature engineering and pipeline process. So here I am in the browser. I've gone ahead and loaded a subsample of the data we were looking at. What I've done just for demonstration purposes so we can move through this quickly in real time is I have subsampled the facts.json file, randomly sampled 10% of the records, linked those over to the URLs and also to that trained CSV and constructed it into a graph. This results in a graph that has almost 2.5 million nodes with a little over 5 million relationships. Of these 2.5 million nodes, I think somewhere between 30 and 35,000 of them are user nodes, and we were able to get a little over 5,000 same as relationships from that trained CSV file, so the same as entity linkages. To show you what the graph schema looks like, I'll pull up this visualization here. So it's pretty simple. Basically, we have a user node for each unique user ID and a website node for each unique URL. They are connected by this visited relationship, which is where a user is linked to a URL through that event hit. I also have these child of relationships. Basically, the way to think about it is if you can imagine a website, maybe like a online store, you're going to have one main URL, and then you're going to have a ton of other product and service pages underneath that, a bunch of other sub URLs. And that's essentially what this child of relationship is modeling here. It's modeling a hierarchical structure. And I broke out the URLs in this way because it gave me a richer graph with more connections, and ultimately that helped the model perform that we'll be training here in a second. Also, of course, the entity linkages from the trained CSV, I'm calling these a same as relationship type. From here, to show you what a couple users look like in the graph and how they can be connected, we'll take a couple out and visualize them. We will here. So here's two users from the graph. Users can be connected in a couple different ways. So you see both of these users have quite a few different websites that they visited. They can be connected by visiting the same website like you see here, but they can also be connected in some more complex ways. For example, here we have a user that visited this website, and then that website is a child of this other web page that this user visited. So with that website hierarchy, we can get these more complex multi-hop relationships, which makes this graph fairly interesting. And to give you an idea of what the same as relationships look like, we'll go ahead and give this a run. And we'll see here that A lot of these same as relationships are just between two nodes, so we get a lot of these components with just two. And then we get some with three as well, and less frequently we'll get groups of 4 or 5 and above that. Most of them, though, are going to be these pairs of 2s and 3s. So now that we have a little bit of an idea of what this graph looks like, I'll go ahead and run through a few more steps. So the first thing that we're going to do is we're going to prepare the data, basically prepare the graph, do some light feature engineering. From there, we will jump into the pipeline configuration and training the model, and then we'll make it to the prediction and resolution step. So first thing we are going to want to do is create a graph projection, and what this call is going to accomplish, it's going to take the graph from the transactional database, and it's going to move it into an in-memory format where we can run global graph analytics quickly. So for this case, we are going to take in both the user and website nodes, so all the nodes, as well as all the relationship types. And you can see for all the relationship types, I have them oriented as undirected, and that's going to mean that the graph that we're projecting is going to be a completely undirected graph. And that's really just for the types of algorithms that we're going to run. It's going to be better for our intents and purposes to run those on an undirected graph rather than a directed run. So this is going to take just a little bit here to run. Normally this goes by pretty quick. Once we have our projected graph, I am going to now run a feature engineering step. So oftentimes, it'll be better to run these feature engineering steps inside of the pipeline, specifically to avoid data leakage. In this situation, I have to run it before the pipeline because we're going to be using relationships that will later be filtered out when we get to the training step. So there's no threat of data leakage here by this design, and it ends up just being easier to run it before the pipeline. So basically what I'm doing here is I'm running a node embedding. Specifically, I'm running something called FastRP, which stands for Fast Random Projections. And essentially what this is doing is it's looking at the graph structure, specifically the relationship structure of the visited relationships and the child of relationships. So you can think of it like the user activity and the website hierarchical structure. And it's taking that information and it's condensing it down. It's reducing the dimensionality into fixed length feature sets, and it's going to give a feature set to each node inside of the graph. So each node is going to end up with a fixed length embedding vector. And the basic idea is that if two nodes have a similar or related structure through these visited and child of relationships inside of the graph, they're also going to have embeddings that are going to be close together. At least that's what we're aiming for. And I'm not going to go into it into a whole lot of depth, but sometimes with these node embeddings, you're going to want to tweak some things outside of just the default settings. So I played around with the iteration weights and the embedding dimensions. You'll find that sometimes just running these directly with the default settings, you're not going to get quite what you want. So you might have to tune some things here. Once that's done, we'll go ahead and get started configuring our pipeline. So going to, as a first step, just instantiate the pipeline. You're going to see when I do that, I'll get a split config and a parameter space with default settings. We are going to adjust these as we go along to make them more what we're going to want for our example here. So the first thing we're going to do after we've instantiated the pipeline is add a link feature. And this link feature is going to be calculated off of that FastRP embedding that we made. And what's going on here is a link feature is essentially something that gets calculated on pairs of nodes, right? So if we're looking at a pair of users, what I'm saying here is calculate the L2 distance between the embedding vectors and use that L2 distance as a feature of the graph. And because these embeddings can be used to represent similarity between nodes, it's highly likely that those features will be predictive when it comes to creating entity linkages or same as relationships. So that's why I included that. I'm going to go ahead and also add a different link feature here, also calculated off the embedding. In this case, instead of using L2, I'm going to also use this cosine distance. You can check our documentation if you want more details on it. It's just another way to calculate distance between vectors, and I found that having both of them can really improve the predictive performance of the model. From there, we're going to configure the data splitting. Now, for this, you'll see we have a test fraction and a train fraction. This is going to map to your conventional concepts around a train set and a test set in a classical machine learning pipeline. You'll see here that the numbers I have don't add up to 1. So the extra 40% of the data set is actually allocated to something called a feature input set. And that's what the pipeline uses to avoid data leakage, so that if we did have any features which were calculated off of, in any way, off of the same as relationships, that set could then be used to avoid this circular relationship that we'll have between our output data and our input features. In this case, we don't really need it because of the way the FastRP embeddings were calculated. We didn't use the same as relationships, but nonetheless, I'll demonstrate here where we can leave out some data for that. Also, we have the negative sample ratio. This, as its name implies, controls how the rate of sampling for our negative examples. A negative example in this case is going to be any two user nodes that do not already have a same as relationship between them. I set this to 2, so it's going to sample those at twice the rate as it has positive relationships. I'm keeping it a pretty low number just for demonstration purposes. You may want to consider setting this higher if you were working with other real-world examples. Generally, you want to represent the imbalance if you can inside of these models rather than trying to balance them. If I set it a little higher here, it would just take the model a few more minutes to run. And as I want to move through this quickly in real time, for me right now, it's just better to keep this lower. So once we have that, we will configure our model parameters. And our model parameters, these are going to be like the conventional hyperparameters for a machine learning model. So things like penalty, patience, epochs, the tolerance. In this case, I have 2 different sets, so it's basically going to run 2 different models with these different hyperparameters, and it's going to choose the best one. I'm not doing anything super exciting here. I could add more models if I wanted to, but basically one model has a small penalty, the other doesn't, and there's a difference in the number of max epochs. So I'll go ahead and add this to the configuration. Once I'm done with that, I have all the configuration I want, and now I'm ready to train my model. So once I hit the train button, it'll go ahead and get started. You'll see here some of the important things that I'm doing. For one, I am filtering the graph down to just the node label of user and just the relation type of same as. And that's to control what I'm trying to predict, right? I'm only interested in this case in predicting same as relationships between users, nothing else, which is why those filters exist. Also, a negative class weight. There's a couple different ways to set this. You can check our documentation here. I'm just balancing it so that when multiplied by the sampling ratio, they equal 1. And that just gives me a pretty consistent interpretation of the metric that we're going to get out here for model scoring in a second. It just changes how the model is scored when we're working with precision and recall. Should be done here, hopefully in just a few more seconds. Ready? Awesome. So you'll see here we get a score of, on the test graph, so on the test set, we get a score of what rounds to just around 0.94. So this is actually not an accuracy metric, and that's pretty important. What this is the area under the precision recall curve. So it's measuring the trade-off between precision and recall. And in this example, it's for imbalanced data sets, which link prediction problems often are, it's better to use the precision recall curve just because that's often the type of trade-off that we're interested in analyzing when data sets get highly imbalanced. In this case, I've scored fairly high here. The maximum number is 1 for this, so I've got around 0.94. And I'd say that that's pretty good given that I haven't, given the amount of time essentially that I've put into putting this demo together. It didn't take me very long to sort of pick some very simple configuration and features to engineer to get here. But I would strongly recommend that you look at our documentation because, again, the way that you choose this, there's a couple other different ways to do it where the interpretation of the area under the curve for precision recall could change. Right now, it's just looking at that trade-off given how I've balanced the data set for training. Alrighty, so once we have that trained, the model is now saved. It saved the model with the penalty, by the way. That one did a little bit better. And now we can take a look at prediction. So once the model's trained, we can run a command like this. And what this is saying is look through all the combinations or pairs of user nodes in the graph that do not currently have a same as relationship, but probably should according to the model. And with this top n command here, we're saying take the 20 most probable pairs and according to the model that should have a same as relationship between them. I could set a threshold here to say they also need a minimum probability, say, hey, don't give me anything with lower than like 85% or 80% or something. It's not quite going to be necessary here, and we'll kind of walk through that in a couple more steps. This step here does take a few minutes to run, so I did actually train a very similar model before this, so we can, and I pre-ran this command, so we can jump right in after we've already casted these mutations to the projected graph. Once they're in the projected graph, what we can do with those predicted relationships is we can write them back to the actual database so that we can visualize and query them easily. So it's a pretty simple command to do that here, the same as predicted relationships. I'm also going to add the predicted probability from the model so we can see that as a property of the relationship. Another step down here, because the projection is undirected, when we write the same as predicted links back to the database, which is always directed, we're going to get a situation where we have duplicate relationships. Basically, between each pair, we're going to have a relationship going in each direction. We're just going to delete half of those, and we don't really care about the resulting direction of the one that's left. We just care that we get one relationship between each of the given node pairs. So once we have that run, we can visualize those new predicted links. And here they are. You can see that we get these pairs of 2 here. We also get a pair of 3, a pair of 4, and a pair of 5. I have noticed sometimes with this data set and this link prediction model, you will start to get some pretty large clusters. If you notice that happening, there's a few things you can do. In this specific example, we're only really looking at a small subset of the data, both in terms of the records that we sampled, and then we're also leaving some features out from the original source data set, which we could add back in to improve this. But other things include increasing the negative sample ratio. That could sometimes help so that you can have a bigger, you can have essentially more negative examples for the model to learn off of. Also, there are some things we can do in terms of tuning the embeddings where we can penalize the importance of some nodes in the network. I'm not going to go into that in too much detail. If you look at the GDS documentation online and go under the embeddings, you can look into that. And there's quite a few things there that you can change. So there's a lot of steps you can do if this clustering ends up becoming a bit of a problem. You'll see too, I'll bring this into a tabular view just so you can see the predicted probabilities. Here we have the user nodes over here. Well, actually we have user nodes on both sides, but in the middle we have the relationship, the same as predicted relationships, and you can see the probabilities for these. So for most of these, they end up being around 0.84 to 0.85. These are the highest probabilities that it found. And if I scan down, you'll see it's pretty consistent around that number. Just going all the way down to make sure. Yeah, it's all pretty much about that. So once we get done with that, now what we've completed by this point is doing the entity linkage prediction. So we've been able to predict these entity linkages. The next step is to create resolved person IDs and query resolved people out of the graph. And we're going to accomplish that by running an algorithm that will assign unique IDs to each one of these disjoint sets, right? So like this set down here might get a person ID of 1. This one over here might get a person ID of 2, a person ID of 3, so on and so forth. And when we do that, we'll include the same as predicted relationships and also the original same as relationships that we got pre-labeled from the source data set. The algorithm that we will run to do that is called weakly connected components. I've configured this so that instead of doing this in 2 steps, it will estimate this on the projected graph and then write those person IDs directly back to the database. This usually runs fairly quickly, and it did so here. This is a pretty fast algorithm. When that is complete, we can now go ahead and query by those resolved person IDs. So there's lots of different ways you can do this. It's pretty easy to do. One example here, I'm just saying, hey, match all the users that have some same as predicted, a new same as relationship that we predicted connected to them, get all of their person IDs, and then collect the basically the user browsing activity, the website visiting information for those persons. And lastly, consolidate that activity by person ID. And when I run that, I'll go ahead and get a return where I have a person ID. I have all the way here on the right all of the user IDs we know for that person, and a list of the website visiting activity where we have the website here, and then we also have the first timestamp, and the last timestamp is just the summary information that I chose. And we have these for multiple, so if I were to scan down really quickly, you can see we have that person ID, we have this next person ID with its own user IDs, their activity, and you can keep going down the graph, or keep going down the result set rather. And this is useful because this is a pretty easy query to pop for a software developer to put into their API, either delivering something to a front end or talking system to system, where you can deliver these resolved person collection or resolved person views. And that completes our analysis. So I hope you saw that this was fairly simple to go from just getting the data into the graph. Only based on the user activity, we were able to train a machine learning model to create entity linkages, and then we were able to walk through how we can write those entity linkages back to the graph, create resolved person IDs, and then query resolved people out. So let's move on to some follow-up resources. I have a few things here. So starting at the top, there's a GitHub repository which should have everything you need to reproduce the demo that we just went over, including a link to the original source data set, as well as some code to subsample that, move it into Neo4j, and then perform the various algorithms and procedures that we just went over. For the next 2 bullet points, if you are a practitioner and you're interested in more information around graph data science generally, or you want to dig into more depth inside of link prediction or some of the other configuration, tuning, and feature engineering options, strongly encourage you to check out our tutorials as well as our documentation. And lastly, if you have an interest in some of the more business level use cases around entity resolution and where Neo4j has been applied to entity resolution, strongly encourage you to check out that link in the 4th bullet point. Other than that, very much interested in hearing your feedback. My email is there at the bottom of these slides. If you have questions, you're wondering about seeing anything else, you're looking for more detail or more examples around something related to entity resolution, please do not hesitate to reach out. And that's about it from me today. So I hope this was helpful for you, and I wish you have a great rest of your day. Thank you.